No.
Please. Yeah, this one.
No.
So good morning, ladies and gentlemen. I'm going to talk about, I'm going to present you the work I've done with Saintenoy on Coquet on inverting saturated hydraulic conductivity from surface ground penetrating radar, monitoring of water infiltration. So first of all, let's get back to basics. So to resolve the Richard equation, you need a lot of things, but you need a hydraulic conductive function as well as water rotation function. Typically, we use for water rotation function the Mohammad function, and we can determine 4 of the 5 parameters. So 4 of these parameters, we can determine them by water and column. And concerning the last parameter, the saturated hydraulic conductivity, on the field we typically most of the time use infiltrometers, so single ring, double rings, disc infiltrometer, horseshoe, Delphi, so on. But those apparatus, they involve many assumptions, and they do not monitor the waiting front. That's why here we want to use geophysicals method, and I'm going to present you a ground penetrating radar. So I will give you some ideas. So ground penetrating radar is just antenna emitting and receiving electromagnetic waves. So through soils, those waves are propagating inside the soil at a speed which is proportional to the square root of dielectric permittivity. It's the dielectric properties of each medium. So for instance, for sand is equal about 4, and for fresh water is equal to 80.1. So as you can see, we will have a big sensitivity of water. That's why in let's say linking water content to permittivity in petrophysical relations, so for instance top relation or plane relation, we have water content. So what is our aim? Our aim is to retrieve saturated hydraulic conductivity during an infiltration inside a simple ring infiltrator and to monitor this waiting front with GPR. So we are going to study constant and unconstant head infiltration. So let's start with constant head. So we used Hydrus 1D. We modelized 10-minute infiltration of constant head. We set the head to 5 cm and we use the Van Genoosten parameter as presented here. We use the saturated hydraulic conductivity equal to 0.12. Then we ask for 1 profile each 10 seconds, so we obtain 60 water content snapshots. We convert the snapshot to permittivity snapshot using Cream formula, and we obtain 60 permittivity snapshots. The snapshot, we use the snapshot as input of GPR max program. So this program is just resolving Maxwell's equation using finite difference in time domain. So this is a radar run, so it's arrival time. So it corresponds to the time needed to go from the transmitter to reflect to the object, in this case it's a waiting front, and to come back to the receiver. And concerning the horizontal axis is trace number. So one trace corresponds to Y profile, so each traces are separated by 10. So there is 4 reflections. B reflection is a direct wave coming from the transmitter through the air to the receiver. A prime and A bis are multiples reflection. And the A reflection is a waiting front reflection. So as expected, you see that the arrival time of this reflection is increasing during the infiltration because the waiting front is going deeper and deeper. So we can beat this reflection and obtain the arrival time with experimental time. And let's get back to our permittivity profile. So you have to know that GPR received signal is the convolution of the derivative of permittivity with depth, convoluted with the emitting function. So that means that the signal will be maximized when the inverse, where the derivative of depth divided by derivative of permittivity is minimum, and it corresponds to the inflection point of all of those curves. It corresponds to the inflection point of all those curves. So we can compute the arrival time of the wetting front by calculating the time to go to the top of the profile and to one of those curves and to come back. So we will have another way to compute the arrival time of the wetting front. And we can compare, we can compare our peaking on the radagram and our optical path stuff. Optical path is crosses and radagram is width. So it's not perfect. Why is it not perfect? No, it's because of numerical dispersion. So here is optical path, okay? It's as the crosses. And I plotted GPR max peaking for 101 node and for 1001 node. And you see that the differences is decreasing as we are increasing the number of nodes, because the size of the layer is smaller and smaller. So we expect if we are increasing the number of nodes, we are reaching the same results. So based on those facts, we would love to try to retrieve the saturated hydraulic conductivity of our radagram. So we generate saturated hydraulic conductivity, we resolve with charge equation, we obtain water content, we convert them to permittivity, and then we compute the arrival time of the wetting front using optical path, and then we try to minimize the misfit. And we obtain a value of 0.128, and the input value, if you remember, was 0.12. So it's not perfect, but it's a good modeling. So based on this modeling, we've made an experiment. So we made 5 cm of constant head during 10 minutes with the following Van parameter determined by water in column, and we determined as well the initial water content. Then we obtain this radagram. So you see the air reflection here, which corresponds to the wetting front. We pick this reflection and we inverse it. We obtain a value of 0.11 cm per minute. And we compare this value with disk and filtrometer measurement using multipotential. We obtain a value of 0.11. So that's perfect. Thank you. No. We have to talk about uncertainties. So we've made some kind of rough uncertainties. We didn't know yet how to quantify those uncertainties, how to, let's say, add those uncertainties. So we've made simple quadratic summation of each error on Van Genooten parameter, and the error on the peaking, and the error on the algorithm, the difference because of numerical dispersion. This is the error of, to compute the error on Van Genooten parameter, we compute the wetting front using the upper boundary of alpha max, and we make the difference between the alpha, the value of alpha we use with this value of alpha max. And what you see on this graphic, it's alpha has a huge influence on the error. So alpha has a huge influence on the wetting front arrival time. And sorry, using that we obtain the huge, not huge, let's say wide range of possible value of saturated hydraulic conductivity, better than the full. So we made another one, and constant head infiltration. So this time we set atmospheric boundary condition with no rain, no evaporation. But we set the first node to 5 cm. And then we've done the same business, computing water content profile, transforming them to permittivity profile, and here's the radagram. So as you can see, after the 43rd traces, all the 5 cm of water have been infiltrated. So drainage starts, and the permittivity is decreasing, so the speed of the electromagnetic wave is increasing. So the arrival time comes earlier and earlier. Then we try on our modeling to invert as well the saturated hydraulic conductivity, and we found a value which is still a bit not correct because of numerical dispersion, but we still okay. So we made as well an experiment, and still the same on the same field using the same Van Genooten parameter, but this time the head was unconstant, and we add this reflection. We picked it and we tried to invert it, and we obtained a value of 113. We compared with the saturated with the disk infiltration. So we have been able to invert one parameter, but we have seen that uncertainty analysis showed that alpha has a strong influence. So why not inverting alpha and saturated hydraulic conductivity, and why not N as well? So in order to do so, we compute misfit diagram. Misfit diagram is just we suppose initial saturated and residual water content node. And then, if we want to plot such diagram in the gas N plane, we need to fix alpha. So we fixed alpha to 0.019 for it's a modeling case. And then for one total of value gas N, we compute the wetting front arrival time with the optical path to the inflection point. And when we are making the RMS error with GPR max peaking, if you remember the diagrams. Then we obtain those diagrams. So each time Hydrus did not converge, we return always the same value, which is equal to 10. So that's those red dark areas here. And the minimum value is the black star, and the true value is a triangle. So as you can see, it's very difficult to invert n, because the minimum value is parallel to the n axis. But alpha and ks exhibit a nice correlation, so we could invert them. And we have been doing the same for unconstant head. It's more or less the same case. But as the last case, I would love to show you the unconstant head case. But this time, we set variable condition, boundary condition, which means that we monitor the layer of water. We note the layer of water. So it is based on experiment. And then we use it in Hydrus. And as you can see, Hydrus converge much more often. It is still difficult to invert n, because n is directly proportional to the slope of the water content profile, and we are using this slope during our repass algorithm as an inflection point. So that's why it's still difficult. It's really dependent on the accuracy of our inflection point determination. So we have been able to monitor the displacement of the working front with a standard GPR equipment, and we have to, let's say, make a real uncertainty analysis on variably-Newton parameter. And concerning the free inversion parameter, prior study for Monte Carlo or other inversion, we have problem with n because of our repass algorithm. And obviously, infiltration is not one dimension. So I'm working currently to 2D dimension and 3D dimension, but it takes a bit more time. And we have to test the method in other soils than sun or lucid soil. We have been working on sun and lucid soil, it works, but we need to do it in other funny soil. And we would love to take into account the water level to see if the GPR max data are marginal or if there are enough to invert everything. So thank you for your attention. Question? Question?
Could you show those graph where you show that?
Which
this
one?
one, yeah.
This one.
You see, if I would be doing this sensitivity analysis, I would really focus on the interval between 1 and 3, because who cares what's happening above 3?
Yeah, I just wanted to see. I mean, I wanted to see if I have no prior information on that, and I wanted to see all the, let's say, all the range, because in the field we found a value of alpha which was quite huge, about 7. It's huge, and that's why I wanted to go, let's say, go to 10, and how to see how Hydrus evolve. And if you, that's funny because I wanted to talk when we are in huge value of n, you see that Hydrus did not converge. Strangely.
But that n value is extremely high.
Yeah, that's extremely high. Yeah.
This is Fontainebleau sense.
Sure, I'm working on
very narrow
Fontainebleau.
pore-size distribution.
I'm working on Fontainebleau sense, sure. Yeah. So that's
so
why
most soils having an n value larger than about 3 or 4, they're already.
Yeah. No, you're right. It's just.
I mean, the
slope
the
is
saddle is completely horizontal.
So
I have to concentrate in a small range, sure.
So maybe n can be identified, except not in that.
Sure, but I wanted to do it in the right range to see if it's possible. My transmitter was going to concentrate on it.
Use a normal soil.
No differential.
Not the French one.
Any other questions? Thanks.